So welcome everyone to this first webinar in a series of webinar that we are going to host. So this one is on an open source toolbox that we made within Energyville, within Etch. And it allows you to do frequency domain analysis of EMT models. So in this webinar, what we actually want to do is to guide you through what frequency domain analysis is, why it is important or has really become important in power systems over the last decade, and the capabilities that we have built into this open source toolbox, together with some small examples as to what the toolbox is able to do. I will, give the floor to Fran later on, but first I would like to just say a few words about who we are at Etch. So we are co-hosting this seminar together with our local student branch and the PES chapter of that student branch and the CRNGN network. All of them. Fran is the presenter of today's seminar, is quite active. And at Etch, so that's our competence hub. It stands for the Energy Transmission Competence Hub. It started out of Energyville, which is a research collaboration between KU Leuven as a university, University of Hasselt, and then Vito and IMEC as national labs. And within that research collaboration, we focus heavily also on the transmission network. What we're doing at Etch is pioneering research in the field of future-proofing our electricity networks for a large-scale integration of HVDC technology and underground cables. So we focus on different things. The main focus here, of course, is research. We also focus on training. We're building a lab infrastructure with this new competence hub, and we're also setting up an industrial ecosystem because we think it's really key for the energy transition to happen, to collaborate, so that we actually bring different actors together to make it happen, and that we also share knowledge amongst the different stakeholders. And also the development of this open source tool is, let's say, within that philosophy. So the four activities that we focus on within Etch is, well, a network where we will see more underground cables, which brings challenges to the system, protection of such systems, control interactions with. The link to the competence center is on the slide here. And without further ado, Fran, I would like to hand over the floor then to you for the technical part of the seminar.
Okay. Thanks for the introduction, Jeff. I hope everyone can hear me clearly. So basically, today we will go through a short introduction where we're talking about frequency domain methods, stability, and so on. And then we will introduce what is frequency domain, stability analysis, what kind of tools we can use within this framework. We'll explain a bit the open source tool that is already available, and then we'll guide you through some examples before finishing with summary and conclusions. Depending on the time, we'll have some margin for questions and answers, so don't hesitate to use the box dedicated for that. Okay, so basically, as you might all know, we have been seeing increased oscillations in the power system recently due to the integration of power converters. And these have different systems involved. So traditional maybe railway systems were the ones where converters were dominating, and then wind farms, renewable, and HVDC systems took the lead. And we have been seeing all around the world subsynchronous oscillations in Australia with widespread impact. Also in Scotland, related to some offshore wind farms. I think at a different frequency range now in the kilohertz range. You might also be familiar with some harmonic instability issues in HVDC systems. And similarly, in the US, they have also observed this problem, similar problems with wind farms and other converter-based assets. So these kind of problems, they were not happening so often before. And the key aspect to notice is that in all of them, there are converters involved. So if we want to reach our carbon neutral goals, we need to do better than this. We need to prevent this from happening in the future and study this in a more efficient way. So in order to do that, what we think is frequency domain methods are a good way of going about this problem, because you can study a wide range of dynamic phenomena from the subsynchronous region up to kilohertz range, where maybe the controls can decrease the damping of existing resonances, and in a setting where several units can also interact with each other. Frequency domain methods also allow you to study systems which include black box models. So if you don't have a mathematical description of your system available, you can still study it and obtain very relevant information. And black box models are fundamental to design HVDC systems, as we have been seeing lately. However, they are a bit more complex to analyze than the white box descriptions. However, frequency domain methods can be very meaningful, and they can bring device level and system level insights and mitigation. It's also modular, so if you are only interested in a specific frequency range, you can just focus on that and neglect the rest of the dynamics. Also, it allows you to study the system in a selective manner, so you can aggregate parts of it directly, and you don't need to care about the order of the system that you aggregate. So in that sense, it's quite scalable. And most importantly, it applies to small signal phenomena. Most of the problems that we have been seeing so far in the previous slide, they are small signal related. So they start as a small signal instability that grows until some nonlinearity is hit, and then the system keeps on oscillating until something happens and is disconnected, or there is another trigger that pushes the system somewhere else. And this small signal aspect is very important because most of the operating time of the power system, it's under this regime. So now I will move on to what is frequency domain and review a little bit the basics. So starting really from the basics, what's a transfer function and a frequency response? You can think of it as a box where you have some inputs and some outputs. In this case, we can have a sinusoidal input with specific amplitude and frequency. And at the output, we will have another sinusoidal of the same frequency with a different amplitude and a different phase shift. And these characteristics are those that define the frequency response. So basically, it's just the ratio, it's the transfer function between input and output, will give us a magnitude amplification or attenuation and a phase shift with respect to this input at every frequency. Now, this is the key component, because thanks to this frequency response, we can apply Nyquist to determine the stability of the closed loop system, and also we can compute other interesting properties of the system from its frequency response. So how do we obtain this frequency response, which is the key ingredient here? There are different methods. I think the most intuitive one and basic is sinusoidal excitation, is what I just mentioned. You have a sinus at the input, you will have a sinus at the output. But you can also use other techniques like pseudo-random binary sequence, Gaussian pulse excitation, and so on, that in the literature have seen increased attention. But here we will focus on sinusoidal. It helps us to get things straight, and also it's the method that provides the highest signal to noise ratio. So we can excite the system with the most energy and get the most information out of it. All right, so how does this sinusoidal excitation work? It's very simple. So basically, we can sweep a signal at the input and measure the signal at the output. And the changes in amplitude and phase will determine this transfer function. And basically, we just divide the output between the input, and that gives us our transfer function. And this would be your single input, single output transfer function, which probably most of you are familiar with. And we go from this time domain sinusoidals to the frequency domain using the fast Fourier transform algorithm, which is also pretty widespread. So now let's go from single input, single output to multi-input, multi-output. Instead of having one input and one output, we can have several. In this example, for instance, we have two. So we have a 2x2 matrix that relates these quantities. And now the device has two inputs. So how do we perturb it to obtain this transfer matrix? Well, from an algebra perspective, we need two linearly independent perturbations to obtain this transfer matrix at every frequency. So a very simple way of going about this is to first perturb one of the inputs while keeping the other undisturbed and record the outputs, which will be currents in our case. We can repeat this again since we'll need two linearly independent perturbations. And now instead we will perturb the other input, the second input, while the first input is undisturbed, and record the currents again. Finally, we again apply fast Fourier transform, and now instead of dividing output or input between output, we do it with a matrix inversion, right? So now it's just the matrix extension of what we did before. All right, so this very simple notion, you are already probably hinting at the fact that here there are voltages and currents. And this is relevant because three-phase power systems are very well defined in terms of DQ frame quantities. And this nicely fits our two input to output description. So our matrix now is a 2x2 matrix. And the same extends to other systems. So if we had, for instance, a power converter, which usually has an AC and a DC side, then we need two quantities for the AC side and one quantity for the DC side. That makes a 3x3 matrix. And this can be generalized to any kind of subsystem based on the description of the subsystem itself. So it can also be generalized to any multi-feed networks. All right. So now that we know how to describe devices or subsystems in the frequency domain, let's go into how do we actually use this for stability analysis. Basically, what we did before was to apply a perturbation. And this perturbation is applied after the system is decoupled from the rest of the subsystems. So you can imagine that we are looking at this device standalone from its connection point or whatever bus of interest. And we can represent it by its admittance. It's what we were using before, relationship between voltages and currents. We can do this not for one device, but for many devices. And then instead of building just one admittance matrix, we will have a block diagonal admittance matrix. And what's at the other side of these partition buses basically is the rest of the network, the rest of the existing network that we are also interested in. And we can also characterize in the frequency domain. And this defines another matrix, the network admittance matrix, the Etch matrix. So there are several ways to obtain this matrix, but basically one of them is analytical models. So if you have an exact description, a mathematical description of your system, then you can compute these frequency responses. If you don't have this, but instead you have an EMT model, then you can also obtain it using the perturbations as we explained before, or any other technique. But eventually you end up having these matrices, and this decoupled way of looking at the system allows you to write it in a feedback manner. And this feedback manner is very useful because we can directly apply generalized Nyquist criteria. Basically, in generalized Nyquist criteria, we look at whether or not this open loop transfer matrix encircles the critical point. If it's single input, single output, is simply the Nyquist response of the transfer function. Here, the generalization is nothing but the eigenvalues. So the eigenvalues of the product of these open loop matrices. And we just look at the critical point and check whether or not this is encircled. And we can do this easily because these subsystems are individually stable. So they have no right half plane poles, and therefore it's a very simplified way of assessing the stability. So quite straightforward. But we cannot not only have a say on whether it's stable or unstable. We can also obtain more information out of this system description. For instance, we can also calculate the oscillatory modes of the system. So, okay, it might be stable or unstable, but in any case, you are interested in how the system will oscillate. And to do that, we simply rearrange the same description that we had before. And what we can observe is that the poles of this closed loop transfer matrix, which is the closed loop impedance, are the roots of this denominator, which, as you can see, it contains the eigenvalues of the state space matrix description. So what this means, and people have done for quite a few decades now, is to apply an eigenvalue composition of this closed loop impedance matrix and look at the points where these values have peaks, because those will be the oscillatory modes of the system. So you can see an example here where we have an eigenvalue decomposition between 1 and 3 kilohertz. And basically we see a few peaks. These peaks will be the oscillations that we would observe if we were to perform a time domain simulation. All right. So now that we know more or less how much information we can extract, we will go to the tool itself. What does the toolbox do exactly? So it's open source because we are based on well-proven state-of-the-art methods. And we also are aware of the importance of accelerating the industrial uptake of academic research. And lastly, we also would like to think that this enables research on new approaches and solutions. So sharing allows us to develop tools faster, right? And also all these well-proven methods, they are not new. If you look at transactions papers, you can find papers from the 70s from Undril and other people studying subsynchronous interactions, right? With a very, very similar description as the one used here. So these are well-established methods by now. And what does the tool incorporate then out of all of these methods? Well, basically the tool allows you to do what we have described before and more. So having an existing EMT model in PSCAD, you can extract the frequency response, different frequency response matrices, and you can apply stability analysis based on these transfer matrices. This includes generalized Nyquist, the oscillation frequency identification, as explained before, and also you can compute other interesting indices such as passivity or singular value decomposition. And additionally, you can also introduce some analytical models. So if you have an analytical model, you can also combine them and the tool will take care of the stability analysis. And this also hints at the fact of how this tool originated. So here in academia, we are very keen on really validating our models. And one way of validating our analytical models is to look at the frequency response in an EMT software. So to do that, we needed to obtain the frequency response. So throughout several projects in the last years, we developed this toolbox progressively, mostly to obtain the frequency response so as to validate our models. And then we added these stability analysis functions that brings it to the state of the art of the methods. So let's go now into how do we obtain the frequency response in this tool. What we do basically is wherever we place the toolbox in the EMT software, the toolbox will decouple it at that point. But regardless, we need to run the system to a steady state. So after we click run on PSCAD, we will have some oscillations. Eventually, the system will stabilize at some point. And at that instance, we connect ideal voltage sources wherever the toolbox is placed. This effectively decouples any subsystem. So in this example, we have two subsystems, but you can imagine a larger network with many of these toolboxes in different buses, and it will decouple all systems, all subsystems at those particular buses. After the decoupling, what we do is we apply sinusoidal perturbations, just very simple injection with high signal-to-noise ratio. And after the system has reached sinusoidal steady state, we simply retrieve this data and apply fast Fourier transform to compute the impedance. And this will give us, at the same time, the frequency response of both subsystems in this example. So you can think of it as if you were looking at both sides at the same time, right? And that's also a little bit where this icon comes from, right? So you are looking at both sides at the same time, and you compute the impedance or the admittance, or the emittance, if you will. Okay, so let's say that you want to compute this not at one frequency, but you want to do this at many frequencies. So for this, there are several functions built in the toolbox, but the most basic one is simply to run these simulations in parallel cores. And this is a functionality that PSCAD enables by default. And additionally, we also can do multi-frequency perturbations. In this example, it's the same as before. So now we have an AC system, so three-phase system. That means that we need two quantities to define it. You can use positive, negative sequence, but in this case, we use the well-established DQ frame. And we apply two linearly independent perturbations. So in the DQ frame, this is very easy. You can just select the first as a D-axis perturbation and the second as a Q-axis perturbation only, and then you can compute the admittances from the measurements like this. As I mentioned before, it's important to validate that the method works, and we used it to validate our models. So for instance, here you can see a synchronous generator-based power plant with different controls and so on. You can see the analytical model in solid lines and the frequency scan obtained with the tool in dotted. So as they perfectly overlap. Similarly, you can study other subsystems. For instance, this is an aggregated offshore wind farm, so just a two-level converter, let's say, and you can also observe the good agreement. And of course, you can do this for any kind of subsystem. For instance, if you were to look at an MMC, which has both AC and DC side, you need its 3x3 matrix, and you can obtain it in PSCAD. Now you don't only have one analysis point, which would be the AC in the previous examples, but now you also have a DC side. So you just place two of these toolboxes, one at the AC side of the converter and the other at the DC side of the MMC. And basically the toolbox does the rest for you. And you can observe here in this figure how the analytical model, which is a simple multiple DQ frame model, also matches pretty well with the EMT results. Okay, and this is just one example for one device, but in fact, the idea is to use all of this in a system-wide manner. So how do we do that? We can measure several subsystems simultaneously, as mentioned before, and this is also validated from different points of analysis. So for instance, let's take this system that is a little bit more complicated than just one device. And now what you can do is you can partition this system at DC bus 1. You would have one subsystem to the right, which is the one enclosed in a red square, and another enclosed in a blue one. So you would scan both of them simultaneously, and you would capture the dynamics of both sides through the MMC on the case of the right, and through the rest of the DC grid on the blue case. And you can see, since the dashed lines and the solid lines overlap, again, there is a good agreement between analytical models and the tool. In addition, for all of these tests, we try to use as good models as possible. So we also incorporated the frequency-dependent models of the cables and the overhead lines. That's why you see some modes on the frequency response there at higher frequencies. But you can also partition the system at different points. For instance, you can now decide, okay, I want to have more detailed information, so I would like to obtain the frequency response from all the DC terminals. And then you do, let's say, a DC side specific study. So in this case, you would still get the same frequency response from the subsystem on the right, but now the subsystem on the left encapsulates a larger AC grid. And therefore, since we have 2 points of analysis which are coupled through the AC grid, we would need to use a 2x2 matrix. And overall, the passive DC network, it's described by a 3x3 matrix since we have 3 terminals. What you can see on the right plots is how the analytical model, using this frequency-dependent description of the components in solid lines, very well agrees with the cross, which represent the PSCAD data extracted with the set tool. All right, so this is for the versatility, but now let's move into an actual study case. I will use the same example here. So let me introduce a bit better what is this system about. We have a 3-terminal HVDC network, as you already observed, which on the left side has a parallel AC cable connected to it. We have an aggregated offshore wind farm and 2 asynchronous grids. So how do we study this system in the frequency domain? Basically, what we can do is to partition the system at every terminal. This is the general case, and is perhaps it's a good guideline for simple systems, because then we can characterize the active devices very well. So here you can see that I have grouped together the passive network, including the overhead lines, cables, and other shunt components. And all the other components, such as AC sources and loads and HVDC converters, they belong to another subsystem, which is grayed out. And how do you do this in practice? So in PSCAD, basically you would just insert these green boxes, which correspond to the toolbox scanning points for the AC partition points, and you would put the pink one for the DC side. So in this way, you effectively decouple the system and at all of these points simultaneously. And once you specify the names of these components and some basic parameters, then the toolbox does the rest. And basically, what would be the result? You would obtain the Etch admittance matrix on the one side. So here we are looking just at the sparsity. What we can see very clearly is the AC system on the right. So this is a point-to-point simple overhead line connection. So it's described by a 4x4 matrix. Then we can also observe the DC grid, basically, where we have 2 DC cables and terminal 3 and terminal 1 are not connected. That's also visible here. And the rest corresponds to the other AC system. Again, here you can observe the validation with analytical models that it gives a very good agreement. And lastly, as I mentioned before, so the larger AC grid can be seen in the middle of the Etch admittance matrix. We also obtain, of course, the admittance, the block diagonal admittance containing the components in gray, which are the active components, generally speaking. And you can clearly identify the MMCs, right? These are characterized by the 3x3 matrix. We also have the 2 AC grid equivalent, which in this case are just simple Thevenin equivalents, and also the offshore wind farm. So now that we have the frequency domain characterization, let's say, we can assess the stability. So let's apply Nyquist as introduced before. Here, what we can see is this eigenloci. We are looking at the Nyquist plot, or the generalized Nyquist plot, if you will. And what we can observe is that none of these curves encircles the critical point, the -1. So this corresponds to a stable case. And in addition, even though it's stable, we can look at how much it oscillates and what is the oscillatory frequency. So we can already observe that there is a peak in this orange closed loop eigenvalue, or let's say modal impedance. around 60 Hertz, but the system is stable. So just to demonstrate that the tool is also able to observe an unstable case, we can force the power control a little bit to the limit and change the parameters on 1 MMC. And now we can run again Nyquist. And now what we observed is that the blue eigenloci encircles the critical point. So now it corresponds to an unstable case. And furthermore, in the oscillatory modes on the right, we can see a peak, a very sharp peak around 63 Hertz. So based on this, we can predict that the unstable case will have an oscillatory frequency of 63 Hertz. And now we can just validate this single case with a PSCAD simulation. So basically, we can change the system parameters and apply a small load step after 5 seconds. And what you can see here is that in one case, basically, the signals oscillate and the oscillation grows unbounded with an oscillatory frequency of 63 Hertz as the spectrum in the bottom shows. So this is a very simple case, let's say, of a multi-terminal analysis. And now I will move forward with another example, maybe more simple in what we are studying, but different in the sense of what we are showing. So let's look at a converter connected to a weak grid. Maybe for you this will be boring because you see the term weak grid everywhere, but it's relevant nonetheless. So let's consider this system, which in PSCAD looks like this. We just have a two-level converter, simple Thevenin equivalent, and we place right in the middle our toolbox library. And what we would like to do now is we just run the script, and what we obtain directly is the frequency response. So we obtain the frequency response of the converter side and the grid side simultaneously. In addition, we can apply Nyquist criterion as before and observe that since the critical point is not encircled, then the system is stable. In addition, the toolbox also provides as a result the oscillatory modes. So the same thing that we did before, you can observe it directly from the output of the toolbox. And in this case, the peaks are not very sharp, and therefore these are oscillatory modes that are quite well damped. We can also compute the passivity index if you are interested about that. I didn't introduce it before, but basically what the passivity index tells us is that if it's positive, then this device will not introduce stability problems in that frequency range. So what we can deduce from these results is that this converter is passive about 45 Hertz, so it will not introduce any stability problems above this frequency point. Now, the non-passive frequency region doesn't necessarily mean that it will be unstable or that there will be problems, but definitely it's a region of attention. And now what do we do with this data? Okay, so it was stable, not very interesting. What I could do is increase the series impedance of the grid, make it even weaker and show that it becomes unstable. But maybe everyone uses this example and probably it's not very realistic. So what I will do instead is add series compensation. So I will add a series capacitor that is classically used to increase transmission system capacity. And I will perform a very simple screening study. Well, I will compute what is the level of series capacitor compensation that I can introduce in the system before reaching a small signal stability. So for this simple screening study, I will neglect the change of the converter dynamics with the operating point. Probably is very small, right? So it's a good assumption for this screening. And what I will do now is for different levels of series compensation, recompute the network side impedance matrix, which is very simple computation, right? Because the original impedance, I already had it from the frequency scan, basically from the toolbox. And now what I will do is to add the series compensation part, which comes in series. And I can do this analytically in a very simple manner. What I will do then is subsequently apply Nyquist again to see if the system is stable or unstable and compute the oscillatory modes and save the results. And I can do this for different levels of series compensation. So basically just a for loop. And eventually I will get a flag, the system is unstable, and I can look at that point. In particular, what we observe is that when the system becomes unstable, the critical point is encircled. So it means it will be unstable. And we can again look at the eigenvalue decomposition to look or to get a better idea of what are the main oscillatory frequencies of this system. And what we can see here is a sharp peak. And this peak again means that there is an oscillatory frequency. And note that this peak happens around 40 Hertz. And this frequency falls within the non-passive region of the converter. So we kind of saw this coming before, or it agrees with the passivity analysis. And what we can do now is to validate these screening study results by performing a single EMT simulation. So we can run the system with this level of series compensation in PSCAD. And basically what we see is that when we increase the level of series compensation after 2 seconds, so it goes from 40, it goes above 45, let's say, above the predicted stability limit. What we can see is that the system starts to oscillate at the predicted frequency, which was 40 Hertz. And these oscillations are sustained. They don't grow unbounded in this case due to the limiters in the converter control. But in any case, this is an unstable system as predicted, an unstable case. All right. So we have gone through 2 examples, one with a multi-terminal system with several MMCs and power converters, this simpler case, let's say, with series compensation analysis. And with the toolbox, you can do more advanced analysis as well. There are other functionalities. You can apply multi-frequency sinusoidal perturbations. So instead of one single frequency, you can speed it up by exciting several frequencies at the same time. And this significantly improves the computational time. We also added some functions for exploiting the symmetry. And perhaps if you are familiar with positive negative sequence, you can understand what this means. But basically, when the systems are symmetric, then you can basically obtain the full matrix without the need of using all the perturbations, because the symmetry reduces the number of linearly independent perturbations needed. In addition, we added a transfer function scan block that we are also actively using. So instead of just characterizing, let's say, the electrical buses, you can just define an input-output to your system and obtain the transfer function. And that's what you can see here on the screen, where we verified that our analytical models for the modulation function of an MMC were matching with what we were simulating in PSCAD. All right. Another point that we are actively working on, and it's basically done, we just need to polish it a bit, is a graphical user interface. So you don't need to run any Python scripts. You just run the software, introduce the data through this user interface, and observe the results directly on the screen. Also through some plots. You can also interactively look at the plots and analyze and save the results, and many other cases. And well, what I have explained so far is the set tool is a useful tool. However, in Etch, I really encourage you to go in the website and look at the open source tools, because what we have seen today, the set tool, this is just the tip of the iceberg, let's say. Here you will find many other toolbox. You can find power models ACDC, it's a Julia package. You can find DSA analysis, which allows you to model systems in a harmonic state space manner in MATLAB, and many more things that will be coming up. Also, some of the simulations or results that you have observed were done with a Julia package that will also be published in the upcoming weeks. to perform frequency domain analysis, in this case with analytical models that will also be open source. And lastly, if you are interested in learning a little bit more about frequency domain analysis, so this webinar was quite packed. We couldn't go in detail into all the aspects. I hope we'll be able to meet in ACDC, where we will also give a tutorial. All right, so let's just wrap up by saying that small signal stability issues have been appearing in converter-based systems all around the world. That frequency domain methods are powerful and mature. Recall that they have been around since the 30s and 40s. And we have incorporated some of this philosophy in the set tool, which fully automates all of these tasks and is also compatible with black box models. We have validated all of our results with respect to analytical models and also with respect to time domain simulations. And another point is that you can do multi-feed AC/DC studies, which, to the best of my knowledge, is the first open source tool that allows you to do this. And it's very versatile, so you can select where you want to study your system, at which points, and how. And probably the most important point is that it's open source. And the idea is that we can continuously develop these methods and improve them by the community. So feel free to go through the Etch website and check out the other open source tools and the set tool, or scan this QR code to directly go to the GitLab where the code is stored. These examples that I introduced today with the Energy Hub, study case, and the series compensation are both available in GitLab, both the PSCAD models and the code used to obtain these results. Together with other usage examples, there is also a point-to-point HVDC link, so you can understand how the tool can be used. And well, that's all from my side. Thank you for your attention, and maybe now we can move to the questions, if there are any.
There are quite some, Fran, that were already posted in the chat.
Let me see. Okay. So there are.
So I guess we will not have time for all questions, but yeah. We
can get back to you by email with the questions that we don't have time to answer now. So thanks for the question. So the first one would be how to approach the computation of the oscillatory modes of the systems where there are several non-rationalities in the modes, so delays, distributed frequency-dependent models. Well, we don't need to rationalize these systems because we don't rely on a state space description, right? Basically, you can still apply all these methods even if your system does not allow for a rational description of it. Then we
indeed, as you point out, because you just apply small signal perturbations based on a time domain model. If the perturbation is small enough.
So Armando also asks if it's possible to extract the frequency response from Simulink EMT models. Well, it is possible, but this tool is not intended for that. It's intended for PSCAD mostly. I am aware of the people at AEMO in Australia. I think they have a similar toolbox for Simulink, so it is certainly possible, and perhaps they will also open source it soon. We don't know, but in any case, the same methodology can be applied in Simulink. Another question is how do you do the DQ transformation? Do you need different rotating frames for each frequency? How do you guarantee phase angle alignment? Okay, so I will start from the end. The phase angle alignment is guaranteed in a post-processing stage. So basically, in order to assess the stability of the interconnected system, you need to refer the different AC side admittances to the same frame. And how do you do that? Well, when they are measured all the admittances are in their local reference frame, but we also measure the steady state angle, and based on this angle, we can just rotate them to a common frame and therefore apply the stability analysis. The DQ transformation is simply Q-lagging DQ transformation, and so far it only considers a steady state positive sequence. So basically that stays fixed, and we don't modify the fundamental frequency of the rotating frames at each frequency. It's not needed. That's the whole idea of the DQ frame, that you don't need to have, that you encapsulate all the frequency couplings back into the same frequencies that you perturb the system. Then the next question would be, when you apply a stiff voltage source at the point of connection, does it work for a device that is controlling the terminal voltage? Would this configuration make the control system not working properly? This is a very good question, and in fact, we observed something like this in some cases. So for instance, in a DC voltage controlling MMC, that's a stiff voltage source at the DC side. But in any case, what would happen if you connect an ideal voltage source to a device that is controlling the same voltage? Well, if this ideal voltage source has the same voltage as that one measured during equilibrium, then you would get to a metastable state. So basically, the only thing you have is a pole at the origin, but that's it. The system is still stable and the operating point will not change. So you can still analyze the system. And when you draw the Nyquist contour, you just make a small indentation over the origin, and that's it. And in any case, we never care about 0 hertz, right? So we don't even need to worry about this small indentation. Okay, next question. Do we need switching model or average model of converter in PSCAD? You can use both. I mean, we have been using the tool internally to validate the average models against switching models. So of course, you can use both models. What is the basis of using voltage perturbation compared to current perturbation? Well, it has two advantages. The first one is that you effectively decouple all the subsystems, because everything is designed to be stable when connected to a voltage source, right? And the second is that it is easier to define the small signal amplitude perturbation, because if you connect a current source, then how do you define the current perturbation, this small current perturbation? However, when we do the voltage perturbations, we define this perturbation in per unit. So basically, if you are measuring 220 kV and then you apply 1% of that, it will be 1% for that bus. At another bus, maybe you have 20 kV, you can still apply 1%, and that 1% will be related to that 20 kV at that bus. So just to summarize, it is easier to define the amplitude of the perturbation. Then next questions, what are the limitations if using this method for studying black box model? I would say the limitations, or the only limitations, are so far just on how good the models are. As I mentioned before, the whole point of going to frequency domain, or one of the advantages, one of the main points, is that you can study black box models. So it is meant to work with black box models, and we have validated with some black box models internally as well. And we also know that the Belgian transmission system operator, ELIA, is also using it for their own studies with their own black box models. So it's definitely useful to study black box models. How do you extract the frequency response in the unstable case? If the system is unstable in the time domain, wouldn't that invalidate the principle of a stable operating point for a small signal injection? This is a very good point indeed. And you need to bear in mind that when we say that the system is unstable, we mean that it is unstable when interconnected to the rest of the power system. Standalone, all subsystems are stable. So there is no issue in this sense. Thanks everyone for your attention. stay tuned for updates on the tool and also other upcoming webinars that we will be organizing, and hope to see you soon. Right.
Thanks for joining.